In the beginning, there was nothing. And then, bang, AEL was born. Astro's Electronics Lab brings you entertaining, sometimes silly videos relating to electronics for your enjoyment. Follow along with his frustrations and antics and maybe learn something in the process.
Greetings, the Astro 30 here yet again with a brand new video, and today I'm going to look at building a stereo preamplifier. However, I'm only going to do the one channel because, well, the other channel is identical and I don't really need, for testing purposes, to build the entire thing. However, this particular design comes from Elliott's Sound Products website. Project number 2, I'll link down below in the description to where you can find the original article that goes more in depth of explanation of this. So what we're going to do is we're going to look at each stage of this preamplifier and I'll just explain its operation. At the front here we've got our main input buffer, and that provides us a gain of 2 because of these resistors here, which is equated to a decibel gain of 6. We come in through a 1 microfarad capacitor here. In this case it's a non-polarized capacitor. I'm showing this as the left in. Goes through this 100k resistor to ground and this 1k stopper resistor into pin 3 of this op amp. Now, all the op amps used in this design are NE 5532s, and the interesting thing about this is it's actually operating at DC gain. In other words, there's no electrolytic capacitor here in the signal path to ground where you would normally see here in the gain stage. He did that for a specific reason, and the reason is to try and keep the DC offset of the op amp extremely low. Now, if you were to include a electrolytic capacitor here, say 10 microfarad, 22 microfarad, what have you, these particular op amps do present a slight DC offset, a few millivolts or so on the output. So that's the reason why he's using DC gain. Some op amps don't actually like operating in DC gain, so it's up to you to experiment with different types of op amps, but in general it should still work. And we'll notice here at the output of pin 1 of the first op amp we've got an L tape out. That goes to a set of RCA sockets on the back of the unit, whatever it is, like just a preamp or a complete amplifier, to connect to the tape in of a tape deck, for instance, or a DAT recorder, what have you. However, as this is operating as a gain of 2, it's going to double whatever the input voltage is. However, on his input selection board, where he's got the various inputs plus the tape output, he's actually going through an L pad filter. So he's got two 4.7k resistors. One goes in series with this line, and the other 4K7 goes to ground, so that gives it an attenuation. So drop it back down to most likely a gain of 1 when all said and done. So not only is this acting as an input buffer for the outside world, it's also acting as a tape out buffer, and it just stops, as he describes in his article, all the nasties that you might get on the input, like if the input leads were shorted. For instance, preceding the output of the first op amp, we're going through a typical Baxandal passive tone control network set up here. He's got two 2K2 resistors here and a 100 nanofarad capacitor across the pot. And there's no resistors on the treble pot, either the ground side or the clockwise side, for whatever reason he chose that for, maybe just to give it a little bit more of a sharper response in the highs. And that comes out of a 10 nanofarad capacitor from its center and a 10k resistor off the center of the base pot, which forms the output side, which is typical. He does say in the article that he originally had it as 10N, but then he changed it to 1 nanofarad. It just gives it a little bit much more of a better presence, I suppose, with a different capacitor. But you can experiment with these values until you get you know, the right tonal balance that you'd like, and like enough boost, enough cut, etc. But in this arrangement, typically at the moment it's plus minus 6 decibels in boost and cut respectively to both controls. However, he says the correction of the bass or the treble pot is very subtle. It's not as noticeable as, you know, if it had more components, designed a little bit better with a 1 kilohertz crossover frequency, etc. Or from using an active backsound or tone control network. But in general, he says that this particular setup should be enough to give balances to the tonal range of the sound, depending on the speakers, the power amplifier used, and the room that it's in. So next we go into the second op-amp stage, which is not operating with DC gain, it's operating with AC gain because of this 10 microfarad capacitor here, which is non-polarized to ground in the feedback path with a 1 mega ohm input set resistor for pin 3. However, I found during testing that resistor wasn't actually necessary, but yeah, it's there. And that just boosts the losses that occur in the passive bass and treble network. Now, this is also operating at a gain of 2, and I found that with a 2.5 input voltage signal at the first op amp, I was getting 5 volt peak to peak out. At the input of this IC here, I was getting about 2.7 volt peak to peak, so we had a gain reduction of, well, half. And this then boosted it up to about 5.2 volt peak to peak at its output. Then from the output we come to this 1K5 resistor, 10 microfarad electrolytic polarized capacitor, for whatever reason you decided to use a polarized capacitor. And that comes into our balance pot here, which is 10K. And the bass and treble pots are also 10K, and every pot that's used in this design is linear. Do not use logarithmic pots. The clockwise position of the balance pot is wired to the left input channel, and the center is wired to ground. The counterclockwise position is then wired to the output of the right hand side channel. And as you rotate this pot fully clockwise, it brings the output signal here down to ground. So that would mean that you'll be balanced fully right. Conversely, if you were to rotate it fully counterclockwise, you would have a slight boost in the left-hand channel and bringing the right-hand channel to ground. So it's a standard, you know, balanced pot arrangement. That then goes into this 100K pot here, and that forms our volume control. And we have this 15K resistor across the center point of the variable pot and ground. And what this essentially does is it turns this linear pot into a logarithmic curve, and that's explained in Rod Elliott's project number 1 about a better volume control using a linear pot, and I'll also link that in the description below too for a better explanation of how that works. And following the volume control is our final gain stage, which in this configuration with these two values gives us a gain of roughly, I think it's 5.7, which is 14 decibels. However, the balance pot in the volume balance network there will give you a loss when the balance pot is at the center of 2.3 decibels. So at the end of the day, this output stage will be operating at roughly about 12.7 decibels. That is also configured as DC gain rather than AC gain. And interestingly, we're going through two 2.2 microfarad capacitors connected in parallel on the output. And he says in the article that that gives a negative 3 dB down response to, I think it was 10 Hertz. Yeah, as I say, the article's linked in the description. You can read it at your own leisure. And finally, we go through a 100 ohm resistor before it comes out the output. Now, this resistor is important because on long cable runs, and it can, when I say long, it can only be as short as, 20 centimeters. This is to prevent this high gain stage from going into oscillation, which and the fact of these NE552s is pretty easy to do. So it just keeps the whole entire preamplifier stable. Without it, you may experience spurious oscillations and can't figure out why. 100 ohm is typical. You could use 220 ohm, 470 ohm, but remember, the higher the resistance, the less gain that's going to be here compared to here. And to stop this this op amp from oscillating, 100 ohm is really all you need. And finally, we're going to look down the bottom here at the power supply section, in inverted commas. All it is basically bulk filtering and DC decoupling of the supply lines. Now, each of these 100 nanofarad capacitors go close to each of the op amps across pins 1 and 8 respectively. That just also helps the each op amp from not going into high frequency oscillation. And the bulk filtering here, these two 10 microfarad capacitors connected across the positive and negative supply rails and ground respectively, help the op amps actually function, because I found without these on the breadboard, and my supply leads were a metre long going back to the power supply, that the op amp would operate for a couple of minutes, and then when I was looking at the oscilloscope trace, that's what I was getting on the screen. So that's a good indication that the supply lines are not filtered correctly. So yeah, I was scratching my head over this and I'm thinking, is it oscillating or is it ringing or what? And then I realised, yeah, I've got to put a capacitor across the power supply rails so it operates correctly. So the bulk filtering is very important. So after that long-winded discussion on how this thing works, I have actually breadboarded it, so we're going to take a look at the breadboard now. And here's the circuit breadboarded. I spent about an hour and a half doing it. It is pretty messy. Over here we've got the treble pot, the bass pot, balance pot. Yes, I know it's a different type of potentiometer, but it's what I have. And our volume pot here. I've got the oscilloscope coming in through this lead here as an input off of the oscillator. It's only because I don't have a long enough, test lead. The oscilloscope's fine in ×1 to do this with. ×10 it becomes a bit noisy. And I'm scoping the output of the 100 ohm resistor, which is off of the third op amp here. And as you guys may notice, I've done a little bit of a modification to the desk here. I've now got this shelving unit, which is not really a shelf. It's one of those tables that you eat meals on when you're lying in bed or sitting on the couch or something. I can't remember exactly what this type of table is called, but it's one of those. So I'll turn the power supply on. I'm already set at 15 volts on both sides. Turn the supplies on and immediately we can see we've got an output. So currently it's saying that we're getting about 4.1 volt peak to peak, and that's with the volume pot set halfway, the tone control pot set halfway, balance set halfway, and an input signal source of about 2.5 volt peak to peak. So if I rotate the volume pot, we can see it goes off the screen. So, and it's still going off the screen. Now according to the oscilloscope there, we've got 21.7 volt peak to peak, but if we notice, it's starting to asymmetrically clip. So it's clipping early towards the positive supply rail than it is the negative rail. So I'll turn that back down. So as we can see, the preamp is actually functioning. Now I do plan to lay out a circuit board for this, so yeah, that's going to be another upcoming video. I'm going to use it probably to power those ETI 480, AEL 480 power amplifier clones. However, we're now going to test the operation of those bass and treble controls. And I'm going to do this using a square wave instead of a sine wave. Now, I'm going to stay at 1 kilohertz, but I'm going to change the type, which I've just gone past, to square. As we can see, it's not completely square, but it's close enough. So now as I rotate the treble pot, we can see what it's doing to the positive going edges and negative going edges of the waveform. So we can see that it kind of looks like the AC/DC symbol for whatever reason. And as I rotate it down to ground, it becomes more sawtooth. Okay, so that's indicating to me that the treble pot is doing something and probably operating where it should be. Now if I play with the bass pot, we can see that nothing happened that way and nothing happened that way, which is interesting because it should. Alright, so what I'm going to do is I'm going to hook it up to an amplifier which just turned itself off, but I'll hook it up to an amplifier and yeah, we'll just see what happens. Alright, it's hooked up to an amplifier. I've still got the oscillator going into the circuit. Yeah, alright, that's interesting. It doesn't appear to sound like the bass pot's doing anything now, which is kind of annoying. Yeah, that's not operating correctly. It shouldn't do that. I've got the feeling I've done something wrong here. But this treble pot should not be shorting the output out. So, yeah, what have I done? Figured the problem. Do not use a ceramic capacitor. Yeah, that gave me a terrible result. This is a 10 nanofarad ceramic. Yeah, I've changed it now to a 1.5 nanofarad MKT capacitor or polyester, and now it's functioning correctly. Okay, so let me hook this back up to the oscilloscope and we'll look at the response with a square wave at 1 kHz going through it, as I was trying to do in the first place, so we can see how the bass and treble controls actually function. Yes, this is raw, I keep my mistakes in. So anyway, I've got a 1 kHz square wave going into the circuit, got roughly 5.5 odd volt peak to peak coming out. It's not a perfect square wave, but that's only just how the filter is interacting with the signal. It would be perfectly square if the thing was not going through that particular network. So if I play with the treble pot, again we can see the peaks here and here on the, well, basically the positive going and the negative going that way. That's with treble up full. With the treble down to ground, That looks like a more expected waveform. It's kind of, I'm not sure how to describe that. If I put it back up, yeah, it's just giving a subtle slope to the positive going peak. So I'll put that back in the center so it's square again, and I'll increase the bass, and that's what I was looking for. See that this side rises and this side lowers, and the slope slopes down that way. That's exactly how the bass and treble pot should interact with each other. And when I put the treble and bass down 0, that's the frequency response we get. And if I put it in full up, there we go. So that's what I was expecting to see. And currently I have a jumper lead connected at the other end of the capacitor because I didn't have one with leads long enough. Anyway, that's beside the point. What I'll do is I'll leave the thing in the center position or flat position, and I'm going to now do a frequency sweep on the circuit just to see what its frequency response curve is. It should be pretty flat between 20 Hertz and 20 kilohertz respectively. And it's a fairly rainy day today, so this is sort of like the perfect thing to do on a rainy day. So I've got an online sweep generator set to 1 Hertz to 30 kilohertz, and as we can see we're getting a signal, but I need to adjust my time base. And what we're looking for is a change in the peak-to-peak voltage as it's going through the scale. Currently we've got around about the 3 volt mark there. So currently at 5 kilohertz we're still roughly in the 3 volt range. I mean, the bass and treble pots are not going to be dead center, let's just get that right. So you may see a slight increase and decrease by a few hundred millivolts. But for my eyes, that's starting to look, or does look, reasonably flat throughout its frequency range. And I would expect it to using op amps anyway. So I'll put this on the lowest time base that I can, and I will restart the test. We're at already a kilohertz, but we can see that the frequency response is remaining relatively flat. There might be a slight ramp up in voltage as it's getting into the high frequencies, but it's not terrible. So I'm quite happy with that frequency response. It's also coming directly off the laptop's AC90 sound card, so you've got the frequency response range of that thing too to keep in mind. But we're already at 10 kilohertz. It's remaining relatively flat, it's not falling off. 13 kilohertz. It's a 2-minute sweep, I believe I put it set to, 120 seconds. So it's going to take a while to get to the 20 kilohertz mark. But the output voltage seems to be remaining pretty steady, so that's got a good frequency response, and we could hear it in the sound output too. Well, I could, the camera won't do it justice. Now we're getting to the 20 kilohertz range. It's starting to fall right off. To the point where it's like just noise. So yeah, I'm going to say that it's a frequency response of 20 Hertz to 20 kilohertz standard. So that's working perfectly fine. So I'm going to conclude this video by saying that I am actually happy with how the results turned out with this thing. It's simple, it works, and yeah, so all I do now is just load a PCB and have it manufactured. If you find there's too much gain, you can always reduce the 10K feedback resistor in the final op amp stage here to lower it down. But because I'm going into an amplifier which is set at a volume level of about 15%, I mean, this is going to spend most of its time up there. I can't be bothered in this test to set up a power amplifier to actually, you know, test where this volume control is going to live. I mean, I can do that in the final setup, but I am going to use a 1.5 nanofarad capacitor in the treble. Because, well, he did say he changed it to 1 nanofarad. 1 nanofarad 5 should be fine. But yeah, so anyway, I hope you enjoyed this video. If you did, please remember to go down below, rate, comment and subscribe if you haven't done so already. Anyway, this is the Astro 30 saying I'll see you later in the next video. Thanks for watching.
Thanks for watching. Please remember to like, comment, subscribe and share the video. I'm Samuel Jones. This has been Astro's Electronics Lab.